All right, ladies and gentlemen, welcome back. So we are going to pick up today really walking through all of the different hormones that your body produces, where they come from, what their basic function is, so on and so forth. Now, today's going to be a little dense, so just kind of sit tight, hang in there. That being said, there's going to be a lot of information here, but as far as AP is concerned, it's not necessarily something that you have to memorize, but the more familiarity that you can have with these hormones, what they do and where they come from, the easier it's going to be to sort of digest that information as it shows up in questions. So let's kind of start at the top of your body and work your way down. So we'll start in your brain and we'll talk first about your posterior pituitary hormones. And from here, you really only have two major hormones that get produced by the posterior pituitary. And these guys are going to work directly on non-endocrine tissues. So they're not going to go and work on other endocrine glands. Instead, they're going to work on other tissues in your body. So the two major hormones that we get from your posterior pituitary is the oxytocin and then your antidiuretic hormone, or ADH. Both of these guys are peptide hormones, so remember kind of what that means in terms of where their receptors are going to be. All right, these guys are water soluble, so their receptors will be on the cell membrane as opposed to internal. So oxytocin, that one works specifically in females, and it will work to stimulate contractions of the uterus, both during menstruation and during childbirth. And they will also play a role in stimulating mammary gland cells to release milk in breast tissue. That one happens to be regulated by your nervous system specifically, so there are feedback loops working to make this particular hormone function. Your antidiuretic hormone is also another peptide, and this one is going to promote the retention of water by your kidneys, so it's really regulated by cell receptors in your body watching and monitoring your water and your salt balance. Your anterior pituitary gland, on the other hand, is a pretty big workhorse. So this one, you've got a whole bunch of hormones that work here, some of which have tropic effects, some of which have non-tropic effects, some of which can have both, depending on the type of cell that they are functioning in coordination with. So it controls the release and inhibition of hormones from your hypothalamus. So if we take a look at the chart here, all of these are peptides or some derivative of a protein. So again, all water-soluble hormones. So receptors will be on the exterior of the cells. If we look at your growth hormone, all right, this one is going to stimulate literally growth, especially of your bones, as well as having some metabolic functions. Prolactin's another one. This one will work in coordination with the oxytocin as well, to specifically, in this case, stimulate milk production and secretion in breast tissue. Your FSH, which stands for follicle stimulating hormone. This one will work in the production of ova or eggs in females, as well as the production of sperm in males. Luteinizing hormone, or LH, also a one that's going to work in terms of stimulation of ovaries or testes, depending on the gender you're talking about. Your thyroid stimulating hormone, or TSH, stimulates specifically your thyroid gland and the hormones that gland will then produce. And then you also have your androcorticotropic hormone, or ACTH. And this one works specifically in your adrenal cortex to secrete glucosteroids. So a lot of these guys are going to come back as we continue working through some of the other endocrine glands today, because they will then produce additional effects, causing other glandular hormones, or in certain cases, to also produce additional hormones that then go have other targeted effects. But if you look, these guys are all regulated by your hypothalamus. So that's what's ultimately making the decision as to whether or not these particular hormones get released. So let's sort of take them little by little here. So let's talk about your growth hormone first. So again, this one is secreted by your anterior pituitary gland, but it has both tropic and non-tropic actions, meaning that it will work directly on endocrine glands, but it also has targets on non-endocrine tissue as well. So your growth hormone promotes growth directly, as well as having a diverse metabolic effect. So it can stimulate, for example, the production of growth factors. Remember that those guys are important as part of your cell division process. So in order to get sort of that go-ahead signal going through cell division, going through your um, interphase, those growth factors have to be promoted and produced and secreted. So growth hormone is one of the ways that we can do this specifically in order to make more cells for growth. Just like anything, there can be over or under expression of these hormones. So, if you get into a situation where a particular individual is excessively producing growth hormone, they may end up with a diagnosis of gigantism. They're big, lanky, um, because they're overproducing, they're making too many cells, stimulating those growth factors. Lack of it could be associated with dwarfism on the opposite side. So let's talk about your thyroid regulation here for a second. So remember that your thyroid is your major gland in your throat. All right. And your thyroid regulation really is going to be part of what we talk about as a hormonal cascade pathway. So, what does that really mean? Well, it means that a hormone gets stimulated, usually by your hypothalamus, which then gets released more often than not from your anterior pituitary, which then goes and acts on other glands in your body. So that's sort of where this cascade effect comes from. That other secondary gland, in this case the thyroid, then produces additional hormones that then go out, work on those targeted cells, and ultimately create that response. So that's what you're seeing here. So brain control, all right, secreting that hormone into your blood, which then goes and works on another gland, which then produces more hormones, which then ultimately produces a response here. So what you're seeing in this particular one is a neurosecretory cell releasing neurohormone, in this case your THR, your troponin releasing hormone, that ends up in your bloodstream directly to your anterior pituitary gland, which then releases your TSH, your thyroid stimulating hormone, which now goes back into your bloodstream again, ultimately to your thyroid gland, where your thyroid gland then produces your T3 and T4 hormones, which then go work on your body tissues, which then increase your cellular metabolism. So lots and lots of pathways here as things get released. But at the same time, we can also regulate these levels a little bit as well. And in fact, this one happens to work all by negative feedback. So here's kind of what I've just talked you through, right? So the release of that thyroid hormone results in this hormonal cascade, and it's involving multiple different secretory glands in your body before you ultimately get to that target cell. So these hormonal cascade pathways typically involve negative feedback because as I get that target cell's response and get the production of, in this case, the T3 and T4 hormones, that feeds back to the anterior pituitary gland to stop the TSH production, and then that also feeds back to the hypothalamus to stop releasing the TRH. And so they get cut off as the stimulus gets stopped or gets counterbalanced. In this case, we're talking about being too cold, so we're going to increase your metabolism in order to warm your body back up. And you've got all of these steps in that pathway in order to do that. While we're on the topic of your thyroid, let's just talk a little bit about the fact that you can have, just like any hormone, over or under production. So if we end up in a situation where we are having too little thyroid production, you would be diagnosed with hypothyroidism. And in fact, this particular disease seems to be becoming more and more common. What does it end up being coordinated with, or symptoms of hypothyroidism? You tend to get unexplained weight gain. You tend to be lethargic, so tired all the time. You tend to have a cold intolerance. On the reverse side of that, you've got hyperthyroidism, or the excess production of those thyroid hormones. And if you look, there's a lot of sort of opposites to this. So excessive weight loss, high temperatures, so you're sweating a lot, also going to cause your heart to beat faster, so you end up with high blood pressure, irritability. Regardless of what's going on, malnutrition seems to be something that we can tie back to alterations in your thyroid function. The question really just becomes to what level is that malnutrition causing those problems, or how much of the dysfunction of the thyroid itself is a result of the malnutrition. So Graves' disease is also a particular disease that is associated with this. This is an autoimmune disease, so your immune cells are actually in there attacking your thyroid and causing the disruption. So Graves' disease is a form of hyperthyroidism. So go back here, right? So you're looking at this high temperature, this excessive weight loss, so on and so forth. One of the things that Graves' disease sort of is antipified by, if it gets to a level where it is untreated long enough, they actually get this protruding eye. So your eyes, you get so much pressure that gets built up from, once again, high blood pressure, right? That it actually causes your eyes to extrude out of their sockets. It's kind of an intense look. If you take a look and go Google some pictures of people with Graves' disease, that's a very common tell. Goiter is another potential disorder of your thyroid. We've talked about this a few times this year, and this is a result of insufficient dietary iodine intake, right? You really don't need a whole lot of iodine in your body. It is a trace element, but you need just enough in order to make the hormones T3 and T4 that your thyroid produces. So without it, your thyroid is unable to produce these hormones, and so you end up getting this enlarged thyroid gland. It swells up. If it swells up big enough, you get this sort of growth on your neck. Sort of think of like an Adam's apple, but bigger, a little more rounder than that. But that's kind of the basic idea. Generally isn't life-threatening, generally doesn't cause too many issues unless it gets really big and then starts to collapse your esophagus. But good news is that for most people, if it gets the iodine intake gets adjusted, they can at least bring down the goiter. It may not necessarily get rid of it completely, but you can sort of reverse some of the effects, at least if it's taken care of early.
Got a case study for you. Let me tell you about Marie. She was a healthy woman in her late 30s. She'd always been an active person, but at some point her energy level just seemed limitless. She was walking the dog 4 times a day, up at 5 in the morning, emailing her coworkers, and at midnight she was still awake, like dusting the ceiling fans. At first she felt great, she was super productive, but soon she started having trouble sleeping. She felt anxious all the time, she lost a lot of weight and noticed that she felt hot and sweaty when no one around her did. She started experiencing heart palpitations. Then one day her vision seemed blurry, and when she looked in the mirror, she was kind of surprised to find that her eyes were actually bulging out of their sockets. So yeah, she finally called a doctor, because, you know, bulging eyeballs. Marie's doctor referred her to an endocrinologist who, after running some tests, determined that the root of her problems was in her thyroid gland. The thyroid is one of the stars of your endocrine system. It's the little butterfly-shaped structure located anterior to your trachea and inferior to the larynx or voice box. It may look cute and unassuming, but don't be fooled. The powerful hormones that it produces influence some of your most important physiological processes. These hormones, and many others, help maintain your chemical homeostasis, the balance and concentrations of substances like calcium, sodium, even water within very narrow ranges so that your body can provide a consistent internal environment for your cells. Your cells and the proteins in them need that stable environment to function, so if your body loses its homeostasis too dramatically, cellular function will stop, and as we say here on Crash Course Anatomy and Physiology, you will stop being alive. So your thyroid helps you avoid such a fate by secreting hormones that regulate many aspects of your body's homeostasis, like body temperature, skin moisture, and your blood's levels of oxygen, calcium, and cholesterol. It should come as no surprise that if the thyroid malfunctions and produces too much or too little of a hormone, it can lead to all sorts of weird and serious symptoms. And yet, thyroid thyroid disorders and the hormonal imbalances that accompany them are pretty common. It's pretty likely that you know at least one person, most likely a woman, who has experienced an issue with a dysfunctional thyroid, and many more of us are walking around with thyroid disorders and haven't even been diagnosed yet. In Marie's case, it turns out that she had Graves' disease, an immune system disorder that results in the overproduction of thyroid hormones, or hyperthyroidism. Although it's just one type of hormone disorder, looking at her symptoms can help us understand just how important, influential, and interconnected hormones are, and why they need to be properly balanced to maintain healthy homeostasis. And I cannot say this enough, homeostasis is life. Last time, we talked about hormone cascades and how a lot of the hormone activity that's bubbling along inside of you is the result of one kind of hormone bossing around the cells that produce another kind of hormone. These pathways typically start with an internal stimulus, often coming from the hypothalamus or pituitary gland, and end in the target glands that release hormones into the blood to get the real work of living done. We've seen how this kind of cascade controls your body's stress response through the hypothalamic pituitary adrenal axis, or HPA axis. Basically, your brain tells your hypothalamus to tell your pituitary to light a fire in your adrenal cortex, and in no time they've shut down digestion, released a bunch of energy, increased your blood pressure, and everything else you need to either fight or flee. And that's great! Your HPA axis is super useful when you are under stress and need to take action. But you do not need your adrenal cortex spouting off all the time. The truth is, much of the more basic, more fundamental business of everyday life is carried out by a different kind of cascade. It's the hypothalamus pituitary thyroid axis, or HPT axis, and it's what sets the thyroid gland into motion so it can regulate just about everything related to your homeostasis. For example, let's say you're caught outside on a cool day and you're underdressed. So let's say you were on a bus, busily texting your bestie, and you got off at a stop while searching for the emoji that most accurately depicted your reaction to the new Avengers movie when you realized that you'd left your jacket on the seat. There's nothing you can do to get your jacket back, but your hormones can do something about your coldness. Now, your nervous system, of course, has its own ways of detecting and signaling a change in temperature, but your endocrine system gets involved as soon as it senses that the temperature of your blood has changed. Your cooler than normal blood flows into your brain's hypothalamus, where it bumps up against temperature-sensitive sensory neurons, which act like a kind of thermostat. Once they detect that the temperature is below target levels, those neurons secrete thyrotropin-releasing hormone, or TRH, into the bloodstream. TRH is a tropic hormone, which means that it gets the hormone cascade started by triggering the release of other hormones. The cascade starts off with just a trickle as TRH goes just a few millimeters to the anterior pituitary, where it hits receptors on cells there, causing it to release thyroid-stimulating hormone, or TSH, into the bloodstream. That then travels down to the thyroid, finds its receptors, and slaps the gland to attention so it releases its own special thyroid hormone into the blood, where it can affect virtually every cell in your body. Like steroids, thyroid hormone is lipid-soluble, so it crosses the membrane of its target cell to bind inside the nucleus. There, it can make the cell either increase, decrease, or maintain its primary function. In this case, since you're feeling chilly, your body needs to stoke the fire a bit, and it does that by burning glucose. In your cells, burning glucose really means breaking it down so its component parts can be used to produce ATP. Thyroid hormone comes into play when it binds to receptors inside the nuclei of your muscle cells, triggering the transcription of DNA that makes the enzymes to break down that glucose. With more of these enzymes flowing around, more glucose is being broken up and more ATP is being produced, which is all a long way of describing the process that we call metabolism. But since the thyroid has increased the amount of chemical reactions going on, it also increased the amount of waste heat that's being generated. So this process has a calorogenic or heat-producing effect that helps warm you up. Now, whether or not you happen to forget your jacket on the bus and found yourself shivering on the way to work, your thyroid hormone produces all kinds of other effects as well, like maintaining your blood pressure, promoting the growth of tissues, and triggering the secretion of digestive juices to keep food moving through your digestive tract, just to name a few. So, thyroid hormone for the win, right? What's not to love? Well, what's important about the whole HTP axis is not just how it works, but also how it knows to turn off. Your glands need negative feedback in order to know when their job is done so they can stop secreting certain hormones. That's where your pituitary and hypothalamus come in. Remember, they're always monitoring hormone levels in your blood. If there's too much thyroid hormone, they both decrease their own hormone production to stop stimulating the thyroid. That, in turn, reduces thyroid hormone levels in the blood and slows down your metabolism again before before you get overheated. At least that's what happens if everything's working the way it should. But there are millions of Maries out there. Plenty of people, maybe even including you, who know full well that hormonal imbalances, thyroid-related or otherwise, happen all the time. Why? Well, thyroid disorders can be caused by lots of things, but in the case of our Marie, it's autoimmune dysfunction. Normally, when you get sick with a virus or bacteria or what have you, your immune system responds by sending out antibodies that target those invaders. Now, we don't fully understand why yet, but if you have something like Graves' disease, your body produces abnormal antibodies that target the cells of your thyroid gland itself. And instead of marking those cells for destruction like antibodies normally do, they do something even more bizarre. They mimic the hormones that the pituitary gland sends out, which bind to the thyroid's receptors. So even though the pituitary dials down its hormone production in an effort to get the thyroid to stop, the thyroid does not get the message because the receptors are still being activated. Basically, the gland never receives any negative feedback, so it just won't quit. And if your thyroid doesn't stop, it's hard for you to stop. So that's why Marie was always hot and sweaty. Her hypothalamus was screaming that she was warm enough, but those antibodies were hijacking the hormone cascade. And she was losing weight even though she was eating all the time because the thyroid hormone was no longer regulating her metabolism properly. But what about those big bulging eyes? Remember those? That was weird. Well, because they're part of the immune response, those disruptive antibodies often cause inflammation, particularly in the tissues around the eyes. In some cases, the swelling can be so severe that the eyes are no longer able to close. Treatment for Graves' disease involves either inhibiting the production of thyroid hormones or blocking their effects, basically getting your body chemistry back in order. The moral of the story is that hormones mean business, and by business I mean living, and by living what I really mean is, and everybody say it together now, homeostasis. In addition to learning to respect your hormones and thanking them for helping you live, hopefully today you learned something about chemical homeostasis and took away a greater understanding of hormone cascades. Specifically, we looked at the hypothalamus-pituitary-thyroid axis, or HPT axis, and all the ways your body can suffer when that system, or your hormones in general, get out of whack. Thank you to our headmaster of learning, Thomas Frank, and to all of our Patreon patrons who help make Crash Course possible through their monthly contributions. If you like Crash Course and want to help us make it available for free for everyone, you can go to patreon.com/crashcourse. Crash Course is filmed in the Dr. Cheryl C. Kinney Crash Course studio. This episode was written by Kathleen Yale, edited by Blake DiPestino, and our consultant is Dr. Brandon Jackson. It was directed by Nicholas Jenkins, the editor is Nicole Sweeney, our sound designer is Michael Aranda, and the graphics team is Thought Cafe.
So if you take a look, right, there's your T3 and T4. They are both amines. The other one that is also produced by your thyroid is calcitonin. And this guy has to do with the regulation of calcium in your blood. Now remember, on the back of your thyroid are 4 additional small glands. These are your parathyroids. And your parathyroid glands produce a parathyroid hormone, or PTH, which also is in connection with the calcium levels in your blood. So if you look, you've got your calcitonin in your thyroid gland that's going to lower your calcium levels. Your parathyroid produces this PTH that then raises it. So they are antagonistic hormones to each other. So they are both regulated by the level of calcium in your blood. And so they also work in a feedback loop. So they are antagonistic hormones that are there designed to maintain homeostasis of the calcium in your blood. So if you take a look, you've got calcium intake channels in your intestines. You've also got uptake in your kidneys. And then it also is stimulated by the potential release of calcium from your bones. So you should have somewhere on the order of about 10 milligrams per 100 milliliters of calcium in your blood at any given point in time. If that blood calcium level is rising, all right, then we're going to stimulate your, or I should say, if the blood level is falling, excuse me, that's going to stimulate your parathyroids to then stimulate the release of calcium from your bones, as well as to stimulate the uptake, meaning the keeping of that calcium from your kidneys as well as from your intestines. But you also need active vitamin D in order to do this. So if you didn't if you've never paid attention to your milk bottles or anything like that, they also talk about it being fortified with vitamin D. That's because in order for your body to take up that calcium, you need that vitamin D in order to do that. It's a coenzyme. All right, but that will then cause your blood levels to rise and bring you back to homeostasis. So your blood calcium levels really are in connection to these two hormones. So as that PTH increases the level of your blood calcium, right, we're releasing the calcium from your bones and from the reabsorption from your kidneys. It does have an indirect effect because it will also stimulate your kidneys to activate vitamin D, which you need to get either from your food, or we also get it from um, being out in the sun. All right, that's what's going to produce the intestinal uptake. But as your calcitonin levels decrease, your level of calcium in your blood, we're going to take that excess calcium then and then stimulate the decomposition or the deposition, I should say, into your bones, and then the secretion by your kidneys. So if we go back to this, right, calcium levels are lowering, so we're going to release this, stimulate the uptake so that we're hanging on to that calcium as we need it. But reverse this arrow, and the opposite would be true with the help of the calcitonin. All right, as your blood levels get too high of calcium, we'll stimulate your calcium to set them back into your bones, as well as for your kidneys to try and release it. One of the things you've got to be careful with, though, is if you've got too high of a calcium level, you don't have enough bone density to uptake that calcium, and or your kidneys aren't able to get rid of it via your urine fast enough. That's what you get kidney stones from. All right, let's move on and talk about control of your blood glucose levels. So once again, a bunch of feedback mechanisms here, right? So your pancreas sits here, all right, your intestine is right here. Here's your duodenum of your small intestine, your stomach would attach here. And then you've got your pancreas. And your pancreas is yet another grouping of endocrine cells here where we produce both your insulin and your glucagon. So insulin's job is to decrease your blood glucose level while the glucagon increases it. And once again, they're antagonistic hormones. They help to maintain that blood glucose. So as glucose levels decrease, we increase the production of one hormone. As they rise, we go through the opposite. Now, their pancreas has these endocrine cells called your pancreatic islets, which include both your alpha and your beta cells here. So the alpha cells, their job is to produce that glucagon. Remember, that one's going to then raise your blood glucose level. Beta cells are there to produce the insulin to lower it. I will warn you that oftentimes, if AP is going to go after a particular feedback mechanism, blood glucose levels are one that they often tend to lean towards. So, if we take a look at how this whole process works, here's your blood glucose levels. Usually, they say you should be somewhere between 70 to 110 milligrams, once again, per 100 mLs of blood. So if we've got a stimulus where your blood glucose levels are on the rise because you've just eaten a giant bowl of pasta, for example, your beta cells then get stimulated and they will release that insulin. That insulin goes out into your blood, all right, encourages your body cells, muscle cells, a lot of times to take up a bunch of glucose from your blood, as well as your liver to take up that and then store it in the form of glycogen, so short-term sugar storage. All right, and that should hopefully bring your blood glucose levels back in check. On the opposite, all right, if in fact your blood glucose levels are falling, right, we're right before lunch and you're all hitting that pre-lunch slump, then the alpha cells now will release the glucagon. What does that do? Well, that preferentially targets your liver to break down that short-term glucose storage, that glycogen, release that glucose back into your blood, and then hopefully bring your blood glucose levels back in check. So once again, that insulin's job is to reduce your blood sugars, so promote the cellular uptake, slow down the glycogen production in your liver, and if necessary, promote fat storage if that level of glucose remains high in your blood for long enough periods of time. The glycogen, on the other hand, does the opposite. So this is going to take the conversion of that short-term sugar storage, that glycogen, and convert it back to glucose in your liver. And again, if those levels stay low enough, long enough, then we may also go after the breakdown of your fats and proteins to reverse their breakdown and also re-release glucose, really going back to glycolysis and reversing the process there. So what are some issues with the control of your blood glucose? Well, diabetes. So diabetes mellitus is an endocrine disorder caused by the deficiency of insulin, or the decreased response to insulin in your tissues. So it can either be a situation where we've got something like type 1 diabetes, insulin dependent type 1 diabetes. This is an autoimmune disorder that specifically goes and ends up destroying your pancreas's beta cells. Remember, your beta cells, their job is to produce that insulin. So I've prevented my body from being able to do the production of the insulin, so I can't regulate those high levels of sugar. Type 2 diabetes, this one is non-insulin dependent. You may also come across this one as adult onset diabetes. And this is a result of not that your body can't produce the insulin, but that the receptors that take up that insulin somehow have lost their sensitivity to the insulin. And as a result, the conversion of that insulin the conversion of that glucose to being taken up by those body cells isn't done as efficiently because the receptors don't really seem to recognize the level of insulin that's there and being produced. So it's not really listening to the signal very well. So there's your quick overview: insulin and glucagon. These guys are your antagonistic hormones that take care of your blood glucose levels. They are also both proteins, so that means those receptors are in fact sitting on the outside of your cells. They're sitting in the cell membrane themselves. All right, we can also talk about the adrenal glands. So these guys are going to really be hormonal responses to stress. So here are your kidneys, okay, and then your adrenal glands sit right on top of those guys. When we look at your adrenal glands, there really are two major pieces to their structure. You've got your medulla, which is sort of the middle, all right, and the inner portion, and then your adrenal cortex that sits on the outside. And when we look at those two pieces, both will produce slightly different hormones. So when we look at your adrenal medulla, so this is the internal portion of your adrenal glands, these guys, the cells here, are really working to produce your epinephrine and your norepinephrine. You may also come across them as adrenaline or noradrenaline. And these guys are both members of a class of compounds called catecholamines, if you've ever come across that. So these guys really are your fight or flight response hormones. So they are secreted really in stress activated impulses. They are there to get you out of a bad situation and get you out of there fast. So what are they going to do? Well, they're going to trigger the release of glucose and fatty acids into your blood. So try and get you those quick energy sources to places like your muscles as fast as possible so that we can go through cellular metabolism, get you that ATP as quick as we need it to in places where they're really going to be necessary. It's also going to increase your oxygen delivery to your body cells, right? We need oxygen to go through cellular respiration to make lots and lots of ATP. So not only do I need the glucose to those cells, muscles, for example, but I also need the oxygen in order to do that as well. It will also direct blood flow towards major organs necessary to get you out of a bad situation. So we'll direct blood flow to places like your heart, your brain, your skeletal muscles, and often deprive that of that blood flow from sort of lesser necessary organs at the time. So taking it away from sort of your rest and digest organs, your skin, your kidneys, your digestive system, that sort of thing. So this is kind of just taking a look at the basic loops here. So here's your adrenal medulla, right? So creating that epinephrine and norepinephrine. Okay, and it's coming ultimately from your hypothalamus, sending that nerve signal down your spinal cord, down to that adrenal medulla, and increasing all of these rates by producing those two hormones. That's all short-term stress. All right, so quick. I'm in a bad situation. I need to get out. I'm in danger. I need to fight my way out, or I need to run away. Long-term stress, however, is going to go over here and work via your ACTH through your anterior pituitary gland and work on your adrenal cortex instead. And that's where we'll talk about mineralocorticoids versus glucocorticoids, and what they.
Hi, it's Mr. Anderson. Today I'm going to talk about the fight or flight reaction. This is one of my favorite videos on YouTube. This is from youtube.com/Russia today. So we got this person here walking down the street. All of a sudden they realize there's a car coming, and then they get out of the way. Now, if I were to keep playing it, the guy jumps out of the car, comes running in this direction. But basically, I want to talk about what's going on. So once this guy sees the car, how does he, number one, get out of the way? And then how does that affect his body? How does that affect the organs and the chemistry and all of that inside his body? And so that whole thing is called the fight or flight. And so when I ask students, how does he get out of the way of the car? The answer is always adrenaline. And the right answer is no, it's not adrenaline. Adrenaline's not going to be able to get there that quickly. And so how does a guy really get out of the way? Well, he's going to see the car coming. He's going to process that in his brain, and then he's going to send a message down his nervous system. That nervous system is going to be attached to muscles, and those muscles are going to have ATP ready to go. And so the way he's able to jump out of the way and not get hit by the car doesn't have anything to do with the fight or flight response. It's simply his nervous system, his muscles, and just responding to that threat immediately. But if you've ever been in a situation like that where you just barely survive an accident or something like that, all of a sudden you feel this rush of just your heart starts beating faster, you're breathing, you feel warm. Now that's part of the fight or flight response, because this guy right here, since he's living in a city, is able to just kind of walk back onto the road and keep about his business. But back in the day, if you were attacked by a mountain lion or somebody else, you had to fight now. You had to flee, or you had to attack the attacker. And so all of that is part of what's called the sympathetic nervous system, or that system inside our body that allows us to fight or flight. And so let's zoom inside this guy and talk a little bit more about how the fight or flight works. And so it's basically centered around his brain. And so in the center of his brain, near the bottom, we have something called the hypothalamus. So the hypothalamus in that area of the brain is essentially going to send a signal. Now that signal, not only are we getting signals that are going to the muscles that allow you to move, but it's going to send a signal all the way down, a nervous signal all the way down here. Because in the center of our adrenal gland, we have something called the adrenal medulla. It's connected nervously to the brain. So the moment he sees that car and realizes he might die, there's a signal being sent to the adrenal medulla, or the center of the adrenal gland. It's going to give off what's called adrenaline. And that adrenaline is epinephrine. Epinephrine is a chemical signal that is going to be attached to the circulatory system, and so it's going to course through the body. So as his heart beats faster and faster and faster, epinephrine is going to flow throughout the rest of the body. Now, epinephrine is not going to go into the cells of the body. It's simply going to, if we say this is a big liver cell, it's simply going to bind to proteins on the surface of those cells. And so what's it going to do to the liver? Well, in the liver, what it's going to do is it's going to trigger a signal transduction pathway that's going to convert glycogen that's found inside the cells of the liver, and it's going to release that as glucose. Why is it doing that? Well, glucose is our energy supply. And so now glucose is going to be coursing through our body along with epinephrine. And so now we have a supply of energy. So we can quickly break down that glucose, get ATP, and we can do more out of it. But what's interesting is that epinephrine is going to go other places in the body. And it's going to have different responses depending on where it goes. And so what is epinephrine going to do to the cells that are in control of the breathing, the cells of the lung? It's going to speed up that breathing rate. What's epinephrine going to do when it goes to the cells of the heart? It's going to speed up the rate of the heartbeat. And so it's going to trigger a signal transduction pathway in the heart that's very similar to the signal transduction pathway that we find in the liver cells. However, it's going to have a different response inside the cells. It's going to not release glucose, but it's going to increase the rate of the beating of those cardiac cells. What do you think it would happen to the digestive system? Well, epinephrine's going to go there. Epinephrine's going to go there as well. But what it's going to do is it's going to vasoconstrict, so it's going to slow down digestion. And so it's going to slow down those blood vessels that feed those areas that allow us to break down and digest food, because when you're getting out of the way of a car or fighting an attacker, you don't really need to concentrate on breaking down that bagel that you ate for breakfast. So it's going to shut that down, but it's going to go to the muscles of your body and it's going to vasodilate, and so it's going to move more blood to those areas. And so our whole body is designed so we can have one signal, that epinephrine, but it can have all these different responses throughout the rest of the body. And so that's going to allow our body to respond to that threat, and that's why your heart races, you breathe faster, your pupils dilate, all that happens, and you can thank epinephrine for that. And it's that chemical response and the different either gene expression or signal transduction pathways that we have as a result. And so I hope that's helpful.
So if we talk about your adrenal cortex, right, this is going to release a family of steroid hormones called corticosteroids, also in response to stress, but now we're talking long-term stress. So your cortex is part of another hormonal cascade pathway. So hypothalamus to anterior pituitary, ultimately to your adrenal cortex. And humans, produce two types of corticosteroids: your glucocorticosteroids, cortisol may be one that you've come across before, where it really influences your glucose metabolism as well as your immune system, as well as your mineral corticoids, androstenedione, for example, that affects your salt and water balance. So both of these produce small amounts of steroid hormones that also function as sex hormones, by the way, which is kind of interesting as well. So if you take a look, right, those mineralocorticoids are going to cause sodium ion and water retention by your kidneys, increase your blood volume and blood pressure. In shorter stints, this isn't necessarily the end of the world, but if you can imagine long-term, and I'm talking really long-term stress situations, this can have a lot of impacts. Increase your blood volume, which increases your blood pressure, which makes your heart work faster and harder, I should say. So you can cause a lot of cardiovascular distress from here. If you look at the glucocorticoids, a lot of potential weight loss, or I should say, not necessarily weight loss, but you're breaking down fats, breaking down proteins, and if you're not burning it off, you can get a lot of sort of fat retention and things like here, and you get some partial suppression of your immune response. So people who are dealing with some really stressful long-term situations can end up putting on weight, can end up suppressing their immune system, so they get sicker more often. So it can kind of end up in a bit of a vicious cycle when these guys are released too often for too long. So if you take a look, there's sort of the end-all be-all. If you look, your epinephrine and norepinephrine, these guys are amines, so that means your cell receptors are on the outside of your cells, but the ones produced by your adrenal cortex are both steroids, so internal reception in your cells is where these guys are going to get taken in, as opposed to being on the outside of the cell. All right, let's talk some sex hormones. So these are going to often be produced by your gonads, or which include your testes and your ovaries. They produce overwhelmingly the largest amount of your sex hormones, which include your androgens, your estrogens, and your progesterones. Now, here's the thing. most people will think androgens, testosterone, that means men, and estrogen is women. But both males and females produce all three categories of hormones. It's just a question of to which proportions. So clearly that those androgens are going to be much higher in males, much lower in females. The estrogens are the opposite, considerably higher in females, much lower in males. But they do all get produced in both sexes. So your testes primarily synthesize those androgens, mainly your testosterone, and that's where we get the maintenance and development of the male reproductive system. Also, side effect to that sort of increased muscle mass and bone mass that we typically see in sort of the general male physical physique. The estrogens, more importantly, your estradiols, are responsible for the maintenance of the female reproductive system and sort of those developmental secondary female characteristics, the wider hips, the more fat retention, the breast production, so on and so forth. In mammals, progesterones, including progesterone more specifically, are also there involved in prepping and maintaining your uterus. And then the synthesis of your sex hormones are also controlled by the FSH, your follicle stimulating hormone, and LH, your luteinizing hormone from the anterior pituitary. So those two hormones and the levels at which they get produced from day to day via that monthly cycle are what sort of ends up triggering menstruation as that cycle progresses each month. So there's your basic rundown. So these guys are all steroids. So once again, internal receptors in the cells as opposed to external. One other little guy to talk about back in your brain is this little itty bitty gland sitting here right above your brainstem, and that's your pineal gland. And your pineal gland is responsible for secreting a hormone called melatonin. And this one's getting a lot of news recently as people are taking melatonin supplements, and the question then becomes how effective are they and at what levels do you need them and can you be dependent? And really the question is we don't know. There's not a whole lot of research out there, at least at this point. But what does your body produce it for? Well, it regulates your light and dark cycles as it's released. So its primary function really is to set your biological clock. How do you know when you should be awake versus when you should be asleep? Well, it depends on how much light is coming into your eyes that will then produce the amount of melatonin that you're supposed to produce. So it's sort of your sleepy hormone. The more darkness your body is experiencing, the more melatonin gets produced, and it should make you sleepy. As opposed to if you're constantly bombarded by light, that melatonin production gets diminished and kind of keeps you awake. So there's a lot of question about people who are staring into TVs and cell phones and computers late into the night hours, that their body's sort of biological rhythm, circadian rhythm, has gotten blown off. So people are taking these melatonin supplements to help them sleep. But like I said, the level of research out there, at least at this point, is kind of minimal. So not a whole lot as to whether those supplements help, but your body does naturally produce it to sort of regulate those cycles. So there again, it's another amine. So that means that the receptors would be on the exterior of your cells for this particular hormone. This is a nice sort of overarching view of all of the hormones, kind of puts them all in one place. So not a bad one to take